Welcome to the Bodhi Academy. My name is Anushka Classo, and in today's video we'll continue with our class 11 chapter 5 thermodynamics. Now in today's video we will learn about some of the important terms that are associated in thermodynamics, especially the terms that are related to enthalpy. Now when we talk about enthalpy, we are going to talk about the various enthalpies that we discuss. We don't only focus on one type of enthalpy, but there is enthalpy of formation, dissociation, all these things we are going to see in this part of the video. Now in a chemical reaction, reactants are converted into products and they are represented by the following reaction that reactants give us product. Now the enthalpy change that accompany a reaction is called as the reaction enthalpy. Okay, so whatever change occurs in a reaction, this change related to the enthalpy, that is known as the reaction enthalpy. So the enthalpy change of a chemical reaction is given by the symbol of delta RH. Now this delta RH tells us that it is the reaction enthalpy. Now this delta RH equals to the sum of enthalpies of the products. Say you have two products that are formed. So you have to add up the both the enthalpies of both the products. Then you also have to find the sum of the enthalpies of the reactants. If say there are two more reactants, add the enthalpies of both and then you have to find the difference between both of them. So sum of enthalpies of products minus sum of enthalpies of reactants. Okay. Then next let's look at standard enthalpy of a reaction. So now previously we spoke about the enthalpy of a reaction. Now how do we define it in terms of standard conditions? Okay, now when we talk about standard conditions, we know we mostly relate to pressure, volume, temperature. Okay, now in this, the standard enthalpy of a reaction is the enthalpy change for a reaction when all the participating substances are in their standard states. So now we say that the standard enthalpy of reaction is considered only when all of the reactants or the substances that are participating in the reaction should be in their standard state. Now that standard state is the standard state of a substance at a specified temperature is its pure form at 1 bar. So we have to mostly focus on this 1 bar of pressure. Next, let's look at what happens to the enthalpy when there is a phase transformation. Phase transformation is basically the state of the substance is changing. Either it is going from solid to liquid or liquid to solid. Now the enthalpy change that accompanies melting of 1 mole of a solid substance in the standard state is called standard enthalpy of fusion or molar enthalpy of fusion. Now here what we are talking about is we are talking about the melting state, that is something solid is going into a liquid form. Now in that 1 mole of solid substance in the standard state is called as the standard enthalpy of fusion. So whatever change that is whatever enthalpy change occurs when 1 mole of a substance is melted, that is known as the standard enthalpy of fusion, or it is also called as the molar enthalpy of fusion. Next, let's look about the enthalpy of vaporization. Vaporization, we know that something is going from liquid to gaseous state. So amount of heat required to vaporize 1 mole of liquid at constant temperature and under standard pressure, that is 1 bar, is called as standard enthalpy of vaporization. So now what we are measuring here, we are measuring the amount of heat that we would require so that we can convert 1 mole of any liquid at constant temperature, as in we are not varying the temperature at all, we are setting it at one temperature and at a constant pressure as well, that is 1 bar. So we measure how much heat is required under these conditions so that 1 mole of liquid can get vaporized. This is known as the standard enthalpy of vaporization, or it is also called as the molar enthalpy of vaporization. Next we have the standard enthalpy of sublimation. Sublimation, we know that a solid sublimes at a constant temperature and under constant pressure. Okay, so standard enthalpy of sublimation is the change in enthalpy when 1 mole of solid substance it directly sublimes at a constant pressure and under standard pressure. Okay, then next we will talk about the standard enthalpy of formation. Okay, Now in a reaction we know something is going to be formed, that is the products that are formed. So the standard enthalpy change for the formation of 1 mole of compound from its elements in the most stable state of aggregation is called a standard molar enthalpy of formation, and its symbol is delta FH naught. Now what it means is that when we are looking at the enthalpy change for this, we look for the formation of 1 mole of compound that is being formed, and here whatever elements which are there or whatever reactants are there, they should be present in their most stable states of aggregation, or also known as the reference states. Only then we call it as the standard molar enthalpy of formation. Next we have a set of equations which are called as the thermochemical equations. Now what are these thermochemical equations? So it is a balanced chemical equation together with the value of its delta RH. Delta RH is the reaction enthalpy, is called as the thermochemical equation. So what they are saying is that a balanced chemical equation along with its reaction enthalpy, along with the value of its reaction enthalpy, that together is called as the thermochemical equation. So here what we are taking the moles of the chemical reaction, as in we are finding the balanced moles, okay, how many moles of each reactant is present, that along with including the values of the reaction enthalpy, that together gives us the thermochemical equation. Now for this thermochemical equation we have some necessary conventions to follow. First one is that the coefficients in a balanced thermochemical equation refer to the number of moles, not the molecules of reactants and products involved in the reaction. Now when we are balancing a certain equation, we write some numbers, right in front of the molecules that are present. Now that numbers do not tell us how many. Now if I say we have H2O, okay, if I have H2O, then say I write 2H2O. Now this does not mean that there are 2 molecules of H2O in thermochemical equations. Here it signifies that it is the number of moles. So it is 2 moles of H2O are present, okay, and not that there are 2 molecules of water. That is a wrong convention. Second is that the numerical value of delta RH naught, it refers to the number of moles of substances specified by an equation. The standard enthalpy change delta RH naught will have units as kilojoules mole inverse. So here now what we are saying is that the numerical value which is there, that is delta RH naught, it refers to what? The number of moles of substance specified by an equation. The delta RH naught is directly related to the number of moles of substances that are present, and that is given by the unit of kilojoules mole inverse. Now let's next look at a very important concept of the Hess's law of constant heat summation. Now we know that enthalpy is a state function. Therefore the change in enthalpy, it is independent of the path that it is taking, okay. It basically only depends on what? The initial state of the reactants and the final state of the product. In other words, enthalpy change for a reaction is same whether it occurs in one step or it occurs in say a multiple series step. Now this may be stated as follows in the form of Hess's law. Now Hess's law defines basically this scenario for us in simple terms. So he says that if a reaction takes place in several steps, then its standard reaction enthalpy is the sum of the standard enthalpies of the intermediate reactions into which the overall reaction may be divided at the same temperature. So now what he is saying, that for a reaction that is taking place, say it has several steps. So then in it, the standard reaction enthalpy that is there, that is delta RH naught, okay, that which is present, we can say that it will be a sum of all the standard enthalpies which are present, delta H naught, whichever is present, of all the intermediate steps. Whatever intermediate steps are there, in that whatever substances are being formed, the sum of all that will give us the standard reaction enthalpy. So here what we are saying now, previously what we had said that it is a state function, so we were not much bothered about what path it is taking. But now here when we are justifying the standard reaction enthalpy, it says that we have to include the standard enthalpies of the intermediate reactions that are occurring in it. So now let's understand the importance of this law with the help of an example. Say you have enthalpy change for the reaction, that is carbon graphite, plus you have half O2 which gives you carbon monoxide. Now we have to find the reaction enthalpy, standard reaction enthalpy. Although now CO is gaseous, is a major product, some CO2 gas will be released out, is always produced in this reaction. Therefore, we cannot measure enthalpy change for the above reaction directly. So now what we are saying, here now only one product is formed. But what we are saying is that when this reaction occurs, there is little amount or even sufficient amount of CO2 that is being liberated. So now over here we cannot directly measure the reaction enthalpy. Why? Because that gas which is being liberated, CO2, we have not found out how much is it. So it is necessary to include that release of that CO2 which is there. Now however, if we can find some other reactions involving related species, it is possible to calculate the enthalpy change for the above reaction. Now let us consider the following reaction. Say you have carbon graphite plus O2 giving CO2. Here what they are saying, the standard reaction enthalpy is minus 393.5 kilojoule mole inverse, and CO plus half O2 giving CO2 again. This is from now CO, okay, this was from CO plus O2 giving CO2, and then from carbon monoxide plus oxygen gives us CO2. Here it is much lesser, minus 283.0 kilojoules mole inverse. Now we have to combine both the reactions in such a way so as to obtain the desired reaction. Now both of them have to be combined so as to we get a reaction which involves both the things that we need. To get 1 mole of CO on the right, we reverse the equation too. So now if we want this on one side, we have to basically reverse this equation, correct? So in this heat is absorbed instead of being released. So the sign changes for delta RH value. So here instead, here the heat was being released, okay, but here now when you reverse the reaction, the heat is going to get absorbed, okay. So here it will become what, CO2 is further going to O2 and CO, okay. Here the heat will be absorbed, so therefore the sign which was over here minus, it will change to positive now. Now adding equation 1 and 3, we get the desired equation. So we have added carbon plus O2 giving CO. Now for this we know delta RH will be equal to what, this value minus 393 and this plus 283, which gives us minus 110.5 kilojoules. So in general we are saying if the enthalpy of overall reaction goes from A to B along with one route is delta RH and delta RH1, delta RH2, it is representing basically how many steps are there, representing enthalpies of reaction leading to the same product. B along with other route, then we have delta RH will be equal to sum of all of those enthalpies. Now this we can represent by C here, A, B, C and D we have, okay. So say our reaction starts from here, we are going from here to here, we have one enthalpy. Then we are going say from here to here, we have another enthalpy. So if you have to find the standard enthalpy, we have to basically find all of this, sum of all of this other enthalpies. So that was Hess's law. So that was it for today's video. I hope you have understood. Please don't forget to like, share and subscribe to the Bodhi Academy.